Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous video, I discussed in detail a type of longitudinal physical wave, namely sound waves. This video will instead focus on a type of transverse physical wave, that is, light. As with sound waves, I will begin again with defining what a light wave is, before discussing what happens when light waves interfere with each other, as well as what happens when they diffract. Light polarization will then be considered, which tells us information about the orientation of the waves. I shall then discuss in detail various properties about light waves, for example the speed of the wave and what the light wave is actually composed of. The frequency spectrum of sound was considered in the last video, and I will do likewise in this video for light. Finally, the portion of the light spectrum that our eyes are sensitive to, namely visible light, will be discussed, and how it relates to light colour. As I described in the last video, our ears are sensitive to sound frequencies from 20 Hz to 20,000 Hz. Sound waves below 20 Hz were known as infrasonic waves, and above 20,000 Hz are known as ultrasonic waves. Therefore, I, in a sense, broke up sound waves into three categories depending upon the frequency. Infrasonic waves at low frequencies, sound waves in the middle that our ears are sensitive to, and ultrasonic waves above that. Light, on the other hand, is not broken up into simply three categories, but is instead broken up into 7 categories. Just to mix things up, instead of looking at the frequency spectrum, I will instead look at the wavelength spectrum of light. This is not anything strange. Remember, the speed of a wave is simply equal to the frequency of the wave multiplied by its wavelength. Therefore, high frequencies correspond to low wavelengths and vice versa. It also turns out that the energy of a light wave is inversely proportional to its wavelength. Therefore, light waves with low wavelength have high energies. Light waves with the lowest wavelength and therefore the largest energies are known as gamma rays. Just above this, in other words, light waves with slightly larger wavelengths are known as X-rays. As they have slightly larger wavelengths, they therefore have slightly smaller frequencies and energy than gamma rays. Next, we have what is known as ultraviolet waves, before moving on to the most important part of the spectrum for the MCAT, which is simply the visible portion of the spectrum, that portion of the spectrum that our eyes are sensitive to. The first band of light waves above which our eyes are sensitive to in terms of wavelength is known as infrared. As we go even higher, we then are looking at what is known as microwaves, before finishing off with the light waves that have the largest wavelength and therefore the lowest energies, known as radio waves. As I stated, there is a relationship between the speed, the frequency, and the wavelength of a wave. The speed of the wave is simply equal to the wave's frequency multiplied by its wavelength. As you may know already, the speed of light is a constant. We represent this constant speed by c, therefore the speed of the wave is simply equal to the constant c. As I stated, this therefore means that this equation v is equal to f multiplied by lambda tells us that the frequency of a light wave is inversely proportional to its wavelength. Thus, as I have been describing, an increasing wavelength corresponds to a decreasing frequency for a light wave. And again, as the energy of a wave is inversely proportional to its wavelength and therefore directly proportional to its frequency, the larger the energy, the larger the frequency and the smaller the wavelength. Therefore, gamma rays have the largest energy, the largest frequency and the smallest wavelength, and radio waves have the smallest energy, the smallest frequency and the largest wavelength. This is all well and good, but what actually are light waves? In the previous video, I defined sound waves as oscillations in particle density, actual mechanical disturbances within a medium. Light waves are instead oscillations in the electromagnetic field. They are oscillations in instead a field. This has nothing to do with particles at all. Because they are oscillations in an electromagnetic field, light is a form of electromagnetic wave. As they are oscillations in a field and have nothing to do with particles, light waves, unlike sound waves, can travel through a vacuum. Also, unlike sound waves that are longitudinal, light waves are instead transverse. That is, their direction of propagation is perpendicular to their direction of oscillation. As you may have guessed by the name electromagnetic field, light waves oscillate in both the electric field and the magnetic field. The shape of such electromagnetic waves are as I've drawn here. The electric field is in one plane, for example the XY plane, and the magnetic field is in another plane, for example the XZ plane. Overall, a light wave is oscillating in both planes, both in the electric field and the magnetic field. This wave is still a transverse wave since this wave is, for example, moving to the right. Both the XY plane and the XZ plane are perpendicular to the direction of propagation. As I already stated, the speed of these electromagnetic waves is constant. It is roughly equal to 3 multiplied by 10 to the 8 meters per second. When I say it is roughly a constant, I mean it is a constant in a vacuum. Light in fact travels at a slightly different speed in different media. However, for the purposes of the MCAT, you may assume that the speed of light in air is also 3 multiplied by 10 to the 8 meters per second. As I also already mentioned, light waves have a very broad frequency and wavelength. Gamma rays can have a wavelength as low as 10 to the minus 16 meters and a frequency as high as 10 to the 24 hertz. On the other end of the spectrum, radio waves can have a wavelength as large as 10 to the 8 meters and frequencies as small as 1 hertz. Of course, the most important part of the spectrum for us humans and for you on the MCAT is that of the visible spectrum, namely the part of the electromagnetic spectrum that our eye is sensitive to. This portion of the spectrum corresponds to wavelengths between roughly 300 and 700 nanometers, in other words 300 and 700 multiplied by 10 to the minus 9 meters. Remembering that the speed of light is constant, it is this 3 multiplied by 10 to the 8 meters per second, I will leave it to you to work out what the frequency range is for the visible spectrum. Within this spectrum is of course all the different colours. What determines what colour light is simply what its wavelength is. For example, light waves in the visible spectrum that have very large wavelengths as I've drawn here will be likely blue or purple. On the opposite end, light with short wavelengths and therefore high frequencies will tend to be orange or red. The colour of light is simply dependent upon the wavelength of that light. What does this mean in terms of objects that we see? Well, an object that is, for example, green is one that absorbs all colours of light except green. It is only the green light that is reflected from that object into our eye. Naturally, objects should then exist that absorb all wavelengths of light. Such objects are called black bodies but are in fact hypothetical. All natural objects will reflect some portion of the electromagnetic spectrum. Now I would like to describe what happens as light spreads out, in particular either around an obstacle or through a narrow slit. This phenomenon is known as diffraction. The simplest example of diffraction is what is known as single-slit diffraction. In this case, light waves simply travel through a narrow opening. To see this, consider the following diagram. What I have drawn in red is some sort of obstacle with a slit in the middle for the light waves to pass through. On the left are the light waves themselves. Rather than drawing the complicated correct sine waves that represent electromagnetic waves, I have instead taken the lazy approach of drawing wavefronts. Wavefronts represent these more complicated sine waves. Assuming that the opening in the obstacle is of the same comparable size as the wavelength of the light, then when passing through that slit, the light waves will diffract. They will spread out as shown here. The narrower that slit is, the more the light waves will diffract and the more they will spread out. After the slit, we can consider placing a lens. A lens is something that we will discuss in more detail in the next video, but it can be used to focus the resulting light waves on the screen. If this is done, a pattern can be seen consisting of both bright and dark fringes, as seen here. The location of the minima of this pattern can actually be calculated given certain quantities. If we know the width of the slit A, the wavelength of the light lambda, and the number of the dark fringe we are looking for, in other words the nth dark fringe from the center, then the angle between the line drawn from the center of the slit to that dark fringe is given by the following formula. The slit width A multiplied by the sine of that angle theta is equal to the number of the fringe n multiplied by the wavelength of light lambda. This equation quite commonly comes up on the MCAT. You can be told, for example, the slit width and the wavelength, and asked what number dark fringe corresponds to a certain angle. We can then consider what happens if we instead have multiple slits. If light waves travel through more than one slit, then they will diffract and then interfere with each other. As they spread out from both slits, they will eventually meet up and there will be wave interference. This will result in a noticeably different pattern than that in single slit systems. A very well-known multiple slit system is that of a double slit system, sometimes known as Young's double slit system after Thomas Young, who first attempted it. The setup is as shown here, where d is the distance between the two slits. We now get a very different pattern because this pattern is instead caused by interference, waves interfering with each other rather than just diffraction. There are regions of constructive interference between light waves, resulting in bright fringes, and regions of destructive interference shown as dark fringes. Again, the positions of the dark fringes, in other words the minima, can be determined if we know certain quantities. The formula this time is the distance between the slits d multiplied by the sine of theta, where theta again means the angle between the horizontal and the line drawn from the point in the middle of the two slits to that dark fringe, is equal to the dark fringe number n plus a half multiplied by the wavelength of the light. Don't worry if this seems like a lot of information in just one or two slides. I will go through a typical MCAT question on this topic at the end of this video. We can also use the concept of diffraction to separate light into different colors. Since, as we've seen, the diffraction pattern is dependent upon the wavelength, the amount by which light is diffracted is dependent upon that wavelength. For example, if you hold a DVD or Blu-ray in your hand, then you can typically see a rainbow pattern. This is because that incident white light, which is composed of many different wavelengths, has been diffracted on the surface of that DVD, the amount by which depended upon the wavelength of each individual wave. Therefore, some waves were diffracted more than others, and we got a spread out of the different colors of light, allowing us to see this rainbow pattern. This is one example of what is known as a diffraction grating. Another example of what can happen under diffraction is what is known as thin film interference. For example, consider the thin outer layer of a soap bubble. Depending upon the wavelength, some light rays will be reflected off the external surface of the bubble, whereas some will be reflected off the internal surface. Some of the light waves that are reflected off the internal surface are then reflected into the path of the other waves, thereby causing wave interference. This interaction will either enhance or reduce the reflected light. Therefore, certain colors will be intensified and others will be reduced. This is what creates the multiple colors seen on that soap bubble. Finally, an important application of diffraction in medicine is that of X-ray diffraction. X-ray diffraction is used to both image molecules and to analyze the structure of proteins. It is done so in the following manner. X-rays are incident on atoms, which are then diffracted into many directions. Detectors placed around the location can then be used to measure both how much that X-ray was diffracted and what the intensity of that diffracted X-ray is. This information can then be used to create 3D pictures of those molecules or proteins. I would like to finish this video by discussing the orientation of the electromagnetic waves themselves. As I showed you in a previous slide, light waves consist of electric fields that are perpendicular to magnetic fields and both perpendicular to the direction of propagation. In my example, I had the electric field in the XY plane, the magnetic field in the XZ plane, and that light wave moving to the right. However, of course, if we have a bunch of light waves, then it does not have to be the case that all of those waves are moving to the right. All that has to be true is the electric and magnetic fields are perpendicular to each other, and both of these portions of the waves are perpendicular to the direction of propagation. If we have hundreds or thousands or millions of waves coming from a source, then these waves can be moving in many different directions. This is represented by what I've drawn here, 6 sets of arrows representing all possible directions, up, down, left, right, back and forth. Typical examples of such light would be sunlight and light from a bulb. This light is said to be what is called unpolarized. Plain polarized light is instead, as you may have guessed, light that exists in only one plane. Of course, we know that's not possible for light. Light oscillates both in the electric field and in the magnetic field perpendicular to that. When we say light is plane polarized, we mean that the electric field of all of the light waves are in one plane. Therefore, it is also true that the magnetic field oscillations are all in the same plane. Okay, so just be careful that you understand what I mean by that. All of the electric fields are in one plane and all of the magnetic fields are in another plane. It does not mean that the electric and the magnetic field oscillations are both in the same plane, only that all of the light waves have their electric fields in the same plane, thereby also having all of their magnetic fields in another same plane. Applications of such plane polarized light are not in the scope of the physics portion of the MCAT, but they do come up in the chemistry portion, for example with regards to stereoisomers. If we wish to turn unpolarized light, for example from the sun, into plane polarized light, we use what is known as a polarizer. As I have shown here, if we have unpolarized light, namely light that has its electric field in all possible 6 directions and passes through a polarizer orientated as shown, then this will result in plane polarized light in the direction of that polarizer. In this case, the electric field will be in the up-down direction. Such polarizers can be seen in, for example, sunglasses, which block out most of the light from the sun by only allowing light of a certain orientation through the sunglasses into your eye. Finally, I would like to discuss a type of polarization which is perhaps more difficult to picture, that of circular polarized light. In circularly polarized light, the amplitude of both the electric and magnetic fields are constant, but their direction is constantly changing, such that there is a helical orientation as I've crudely drawn here. I recommend that if you cannot understand what is going on in this very crudely drawn diagram, to have a look at some images online for circular polarized light, as it can come up on the MCAT. This video was the first of 2 parts on light. In the next video, I will go into more detail about how light propagates through different media known as geometrical optics. Before moving on to this, let us, as always, look at typical MCAT questions on light theory. This first question is testing our knowledge on energy, wavelength and frequency of different parts of the electromagnetic spectrum. It states that light from which part of the electromagnetic spectrum has the highest frequency. Is it X-rays, radio waves, UV or ultraviolet rays, or gamma rays? Well, if you go back to my image of the electromagnetic spectrum, you will see that gamma rays have the shortest wavelength. Since V is equal to F multiplied by lambda, the velocity of the wave is equal to the wave frequency multiplied by its wavelength, and also since the speed of light remains the same in a particular medium, then we know that frequency is inversely proportional to wavelength. Therefore, as gamma rays have the shortest wavelength, they also have the highest frequency. Therefore, the correct answer to this is option D. I also mentioned previously that the higher the frequency, the higher the energy. Therefore, gamma rays also have the most energy, and we shall talk more about the results of this in a future video. This next question is testing our knowledge about diffraction. We are asked which of the following causes diffraction fringes. Is it dispersion, interference, diffraction, or polarization? Well, we just discussed that polarization has to do only with the orientation of the waves. Therefore, this has nothing to do with diffraction and cannot be the answer. Likewise, dispersion, as we shall discuss in the next video, is simply the separation of white light into its different colours as it goes from one medium to another. Therefore, option A also cannot be right. Finally, as I emphasized earlier, diffraction fringes are actually created by wave interference. For example, in the double-slit experiment, waves are diffracted and then interfere with each other, causing a pattern to appear on a screen. Therefore, the correct answer must be option B. Speaking of the double-slit experiment, and as I promised earlier, here is a question involving that equation relating to that experiment. We are told to consider the following scenario. We have light which has a wavelength of 600 nanometers, a slit separation of 0.1 millimeters, and we are also told that the screen is 50 centimeters from the slits. We are then asked what is the distance between the third and the seventh minima on the screen. Is it 1.2 millimeters, 3.2 millimeters, 1.2 centimeters, or 3.2 centimeters? To answer this, the first thing we should do is recall what that equation was. The equation for the double-slit experiment was as follows. D, the separation between the two slits, multiplied by the sine of theta, where theta is the angle between the normal and a line connecting the point in the middle between the two slits to the particular dark fringe, is equal to the dark fringe number n plus a half, all multiplied by the wavelength of the light lambda. Well, what do we know in this equation? We know D, the distance between the slits, that is simply the slit separation 0.1 millimeters. We don't know theta, we're not told any angles in the question. We do in a sense know n because remember the question is asking us the distance between the third and seventh minima, so therefore we have two different n's we can use to work out the answer. And we are also told the wavelength of the light. We are told it is 600 nanometers. Let us now draw a quick diagram to make sure that we understand what we are looking for. Again, on the left we have two slits separated by a distance d. We have a screen on the right, which I will say is a distance capital D away from the slits. We also have that angle theta, which I have already defined. And I will introduce another new variable y, which is the distance from the center of the fringes to the nth dark fringe. Well, we are looking for the distance between the third and seventh minima. In other words, we are looking for y when n is equal to 7 minus y when n is equal to 3. Again though, we do not know anything about the angle theta. We in a sense want to replace the angle theta in that equation somehow with y. Y is something we are looking for and theta is something we don't know and it is not something we are looking for. How will we do this? Well, the easiest way to do this is to use what is known as the small angle approximation. As you can see in our diagram, we have a right angle triangle. If we consider theta the angle we are interested in, then y is the opposite and capital D is the adjacent. Since y is typically much smaller than capital D, remember capital D is the distance between the slits and the screen and is therefore typically a macroscopic quantity, whereas y has something to do with the distance between fringes and is therefore a very small number, we can assume that y is a lot smaller than d. In that case, the small angle approximation can be used. Hopefully you have heard of this approximation before. If not, all it says is the following. If that y is a lot less than that capital D, then the sine of that angle theta is very roughly equal to simply theta and tan of theta. This simply comes from the fact that we are assuming that the hypotenuse of that triangle is very similar to the adjacent. In other words, the hypotenuse is roughly equal to capital D also. Check in your own time that assuming that the hypotenuse is also capital D, that this result follows, that sine of theta is roughly equal to theta and tan of theta. This means that in our equation, we can replace sine of theta by either theta or tan of theta. I'm going to be smart and use tan of theta because, remember, tan of theta is defined as the opposite over the adjacent. In this case, that is y over capital D. One of these quantities y we are interested in calculating, and the other quantity capital D that we know. Therefore, I can replace sine of theta with simply y over capital D. Doing so results in this new formula. The slit separation D multiplied by that quantity we are looking for y divided by the separation between the slits and the screen capital D is equal to the dark fringe number n plus a half all multiplied by the wavelength of the light lambda. I can now rearrange this for this y that we are looking for. Doing so, we get y is equal to n plus a half multiplied by the wavelength lambda multiplied by capital D over the slit separation small d. Let us recall what the question is asking us to find. It is asking us to find the distance between the third and seventh minima. Looking at the diagram and remembering what I've defined y as, this is clearly y when n is equal to 7 minus y when n is equal to 3. Therefore, I can plug in n is equal to 7 and n is equal to 3 and subtract them. Then I get 7 plus a half multiplied by lambda multiplied by capital D over small d minus 3 plus a half multiplied by lambda multiplied by capital D over small d. Of course, the halves in both cases will cancel. We will have a half lambda capital D over small d minus a half lambda capital D over small d. They will cancel, and we will have a 7 minus 3, which is 4. So therefore, we simply get 4 multiplied by lambda multiplied by capital D over small d. Now, finally, we can finish this up by putting in what we know. 4 multiplied by the wavelength of the light, which we are told is 600 nanometers, or 600 multiplied by 10 to the minus 9 meters, multiplied by capital D, the distance between the slits and the screen, which we are told is 50 centimeters or 0.5 meters, divided by the slit separation D, which again we are told is 0.1 millimeters or 0.1 multiplied by 10 to the minus 3 meters. Working this out, we get that the distance between the third and seventh minima is 0.012 meters or 1.2 centimeters. Therefore, our correct answer was option C. This question, as you may have guessed, is as difficult a question as you will get on light in the MCAT. Therefore, if you feel comfortable with this question, I would say you are now ready to move on to the next video. If not, be sure to recap this section by looking back on this video and trying the sample passages we have provided for you. As always, allow me to finish this video by recapping what we learned. I began by reminding you that light is a type of transverse physical wave. The direction of propagation is perpendicular to the direction of oscillation. Just like sound, light is broken up into a spectrum depending upon the wavelength, or if you like, the frequency. Radio waves have the largest wavelength and therefore have the smallest frequency and energy. On the other end of the scale, there are gamma rays, which have the highest energy and frequency and smallest wavelength. In between these two extremes, there are various different branches depending upon the wavelength: microwave, infrared, visible, UV or ultraviolet, and X-rays. I then emphasize the fact that not only are light waves transverse, but they also oscillate in two different planes. The electric field portion of the wave oscillates perpendicular to the magnetic field portion. The direction of propagation of that wave as a whole is then in the third dimension. Also, as light has nothing to do with particles, it is oscillations in the electromagnetic field. Light, unlike sound, can travel through a vacuum. I also stated that for a particular medium, the speed of light is a constant. For a vacuum, that speed is roughly equal to 3 multiplied by 10 to the 8 meters per second, and on the MCAT, you may assume that this is also the speed of light in air. As I just stated a few moments ago, one part of the electromagnetic spectrum is that of the visible spectrum, that range of wavelengths and frequencies that our eye is sensitive to. Our eyes perceive different wavelengths within this spectrum as different colours. A particular colour is purely defined by what the wavelength of that light is. If the colour of an object is, for example, blue, then that object absorbs all colours of light except for blue, which reflects off of that object, with some of that light interacting our eye, making us see that object as blue. Hypothetical objects that absorb all wavelengths of light are known as black body objects. I then described what happens when light diffracts. when it spreads out as it moves around an obstacle or through a slit. I focused this discussion on diffraction on two different scenarios, namely single and double slit diffraction. In both cases, I introduced an equation that allowed us to calculate information about the location of dark and bright fringes. Diffraction grating was then discussed, which explains how rainbow colours can be seen, for example, on a CD or DVD. An application of diffraction was then briefly discussed with regards to X-ray diffraction. Such diffraction allows us to create 3D images of particles on the molecular scale. I then finished this video by describing light polarization, that is, the orientation of light waves. In general, light, for example, from the sun is unpolarized. The light is orientated in many different directions. If we wish to create, for example, plane polarized light, in which all of the electric fields from all of the light waves are in the same plane, then we have to pass that light through what is called a polarizer. I then finished this discussion by mentioning what is known as circular polarized light and recommending that you do some research on such polarized light to make sure you can picture what it looks like. Again, as I stated, this is only the first part in a two-part series about light. In the next video, we will focus in more on the actual propagation of light, in particular as the light goes from one medium to another. As always, I hope this video has been useful to you, and I shall see you guys in the next one.